So on to the fun stuff. If you open your Simcenter Testlab folder, you're going to go into Testlab Environmental, and then we're going to look at, here's online sign reduction, which again is pretty much just like setting up a regular sign test, but we're going to talk about this offline sign reduction. And I've got a sample data set that we can play with. So here we go. Here's it's a whole bunch of stuff that I played with working with this. So what we have here, let's see. I think this is it. Yeah, okay. We'll create a new picture here, and I'll show you. This is all the channels here, and essentially what I did is I ran a sign test on an actual test article with all these different channels, and I measured the COLA channel, but we're also going to do an extra step here. Well, what happens if you didn't get this COLA channel, or the COLA channel is bad or something? You have all this data you still have to process. We're going to talk about that too. But to get started, this is kind of a typical scenario where you have all these different channels and then this COLA signal. And I'm going to change this to real. And we're going to move this strain gauge to the back, so that makes sense. All right. Well, it's a strain sensor, not a strain gauge, but still. So this is what happens in a sign test. This is why you need a COLA. If I zoom in here on the COLA signal, you can see the difference here. So this is the control channel, and this is the COLA channel. Now you can see the COLA channel is a pretty perfect sine wave. And then we see the actual control channel that's measuring has got all this harmonic stuff going on, right? This is the raw data. So that's that maroon trace here. Maybe what I'll do to make it more clear is make a copy of this. I'm just going to take out these other traces. So you can see the COLA channel and the control channel, how noisy that control channel is. That's the actual accelerometer that's being measured. And this is because of all kinds of things, right? It might be some micro vibrations in your fixturing or some rattling that's happening somewhere. This could be cable whip that's going on if you don't have a cable that's secure. We can go in and look.
Yeah, so one of the tricks is to try and get a meaningful amplitude out of that, huh?
Trying to get a meaningful amplitude, and you can also see the problem here. We've got a resonance in our fixture. So you can see how this sine data starts to get real wonky because it's going through a fixture resonance, and we're actually out of phase with our drive signal. So that can be real tricky too. That's why this COLA signal is super important to have. But there's a trick that we can do if we need to. So here we go. We can take all of this. We're going to right click. We're going to replace an input basket. So we have this data here. We're going to go to time data selection, and we're going to add from the input basket all these channels here. We're going to go to offline data reduction, and we hit make a trace list, which is going to pull in the data that we selected here in time data selection. And then it asks you to pick a COLA trace. So we'll just, we'll put up 2 of these channels here. And you can see, so you can see if, well, let's move the focus on this and zoom in a little bit. Okay, so we can start to see here, if we were just taking data from, let's say, our control channel. We'll do that. That makes the most sense. The control channel should know what frequency we're at. Well, that looks a lot better than the one we just had, but still, as we go through resonances, we're going to get oscillations in the control channel, and that's going to give us wonky frequency data, right? Because the controller thinks we're rapidly changing frequency here, when in actuality, that's not what the drive is doing. And if we zoom in even a little bit more, we can see what's happening there. So I was pressing. These oscillations make the processor think that we're crossing our zero axis multiple times, when in reality, that's not what the drive is doing. So if you pick this COLA signal as the actual COLA, you can see this gives you a much different picture of what's happening here. None of these blips are in this signal anymore. So we get a nice smooth COLA trace. Now you can judge the COLA settings here and apply some smoothing factors, and you can change where the crossing level is if you have data that's offset. For instance, if you're not crossing zero, let's say you're offset by 1/10 of a G, you can change that crossing level. Now, theoretically, it shouldn't make a difference, because at any cross level that you pick, the distance between 2 points in a period is theoretically going to remain the same. But again, if you have noise or something like that, you might need to adjust some of these factors. But then you also have your acquisition settings here, and you'd set this min and max frequency to exactly what you set up in your sine sweep. And the controller is going to ignore anything that starts below 6 Hertz, because that's just startup noise. So once we get to 6 Hertz in the COLA signal, then we're going to start to take in and plot data, and then it's going to stop when it gets to 2000. And then the measurements is, again, pretty much the same as what you're going to pick in your controller. And you can choose to calculate FRFs or choose a phase reference. For instance, you might want to process phase via the control channel, and maybe you have an FRF reference via some type of other channel here. But again, I'll just pick control here. And then down here, you're going to put the name that you want to save all this data under. And then last step here is to just hit save. And we start to process the data. Takes a little bit of time. And then the last thing you can do is down here, you can preview the results. So this is SDR analysis 2, sine data reduction. You can look at the spectra, and you can look at all the different processed results here. So now, as a check, let's go back into Navigator. We'll create a new plot. We're in SDR analysis 2, spectra, and we have our control. And I'm going to do log here. It was from 5 to 2000. So here we go. And now what we can do is it was sine data 3, and we'll look at the control spectra here. And you can see they're perfectly on top of each other within reasonable error, of course, right? Now, here's what happens if you don't use the COLA signal. So let's change this COLA. And let's just use a straight control channel. we're going to see these blips in the data, and I'm going to hit there to change the SDR analysis with control cola processed. And we're going to notice a couple things right from the beginning. Right? If you set your control channel to use as cola, you're not going to get a control channel spectrum. I'll show you what I mean by that. I have that process data. CR analysis. This one here. So we have this cola spectrum. So you can change the name and stuff like that, but it's not, you don't get the control spectrum anymore, right? You get something like this, which doesn't really have any useful information in it. So we'll remove that. What we can do is back in this time data selection, if we don't have this cola channel, we can take our control and we can just make a copy of it. So we hit this duplicate channel, and now we have an extra control channel, and we can hit save as, and we're gonna do a new run name. We'll call it demo control cola copy. I'm just making stuff up as I go along here. And now we see that that channel has gone from orange to green, so it's saved here. So now when we do this, we can pick a make trace list again, by the way. You can see we have two copies of this control channel. So now I can pick this copy channel that we made and process the data again. Copy. This will process again. I'm back in Navigator with copy. Look at the spectrum, and now we have this control spectrum. We can pull it in, and it looks all right, but you can see the terrible, terrible errors that we're getting here because of the blips in the control channel.
So you just tried using the control channel in lieu of the cola. Straight up. Yeah.
Straight up. It doesn't work out too well. Now you can try another trick here and try messing.
I was hoping you had a trick.
Yeah.
Or
yeah.
two.
One of the first things that we can try here is here. I'll put this control channel up, and you can see these blips here. So we'll try maybe increasing this hold off rate. Let's increase it to 70%. See what happens. Well, that's reduced it some, but now let's see what happens when we process this. Better.
Basically ignoring some of the blips, more of the blips.
We're basically ignoring some of the blips, right? We're saying that we're not going to measure the frequency again when it starts to oscillate within a certain amount of the frame. But let's see here, if we look at the spectra here, and we're going to pull this control channel in again, well, you see this is just garbage data.
That's so, probably not good.
You've improved the cola signal, but basically you've created some other issues. Yeah, I mean, one of these things is not like the other, right?
You better have another trick.
I do have one more trick. We go back to this time data selection here. And what we can do, I'm just going to hit replace from the input basket again. So this is our original data. And I want to try and apply some filtering to this control channel to try and get some of that high frequency noise out. So what I gotta do is go to Tools and Add-ins. I gotta turn on our time signal calculator, I think it is. Yeah. So you can see, I might have done this already. I have created this bandpass filter. It's a 50th order Butterworth. There's a couple different ones. I haven't tried this with all the different combinations exclusively, but you can see this has some pretty sharp roll off to the frequency there.
And you kind of set it to the frequency sweep range, 5 to 2000 hertz.
5 to 2000 hertz to try and get rid of anything outside that frequency. And we're picking filter mode 2 here, which is not going to affect the phase going on here. So a couple other things. I've picked channel 5, of course, which is the control channel to apply to this, 5 to 2000 hertz. And I'm going to save this as channel 10, and then I'm going to name it COLA bandpass filtered 5 to 2000 hertz. I'm going to hit calculate. It's going to create this. Again, it's orange. And if we display it, it doesn't really look all that different between the two, but we'll take a look in a second here.
Can you like zoom in a little and overlay, or?
Yeah, so for example, right in here, I zoom in, you can see the effect of the filtering here. Here was the original signal, and you could see it. The software looks at this and says, okay, I've got 3 zero crossings here. So that frequency is instantaneously gone much higher than it's supposed to. So you can see how that band, and really probably a low pass filter at 2000 hertz would have done the job too. But as you go through here, you can see how that's affected the high frequency noise riding on that signal. So from here, I'm going to hit a save as, call a copy, call it a bandpass filter, 5 to 2000. And hit OK. And now it's saved that away, and I can go to offline sign data reduction, hit this make trace list again. I have my COLA signal that I'm going to use. And if I change this here, and this hold off rate, I'm going to go back to like a default value.
I can feel the tension building. I'm very curious to see.
Me too. All right, and I'll hit save again here. And now, moment of truth. Let's see how we did. We'll take these other ones out here. This was that awful thing.
Can't see it.
This one here.
Is that because of
that was the raw signal? And now you can see here how much better that bandpass it was. You can see there's not perfect agreement here with the filter data, but it's much better than where we were processing without filtered data, or with trying to attack the problem by fiddling with the COLA processing settings. So that's really the best result, I think, that you can get if you don't have that actual COLA signal.